one of our awesome community members from the DevHeads community, Hemal Chavli, who is going to be walking us through power principles. So powering the system is the topic today. And you're in for a treat. I've been over the slides. Hemal's got a great breakdown. There are a couple of polls. It's an interactive session, and it'll make sure that we go through everything you need to know if you're learning how to design a power circuit. So we'll do a quick overview today, some housekeeping stuff, and get right into the presentation. So this presentation is going to be, I don't know, what do you think, 30, 45 minutes, around there?
Yeah.
And that's going to leave plenty of time for Q&A at the end of the hour. So if you are in the webinar platform called Livestorm, what you're going to want to do is navigate to the bottom of the bottom menu, and there you'll see a questions tab. Hit the questions tab, and you can type questions in there, or just to the right of the questions tab, there's a chat tab, and you can type questions in there too. And we'll get to as many of those as we can in the time we have remaining. If you're viewing us on LinkedIn or elsewhere throughout the internet, just drop your chats, your comments, your questions into whatever the native interface is there, and we'll field them and bring them back in the platform and make sure that we ask Hemal at the end of the hour. It's also a great way to collaborate with other people in the event and from the community. Just start chatting each other up there, and see if you guys can come to resolution on your own and meet some new people potentially. So really quickly, got to go over some things that you can do to help yourself in the event that your platform is not working during the streaming session today. So if you have issues viewing the stream, hearing the audio, or anything else related to the broadcast, try these things out. So first thing is check your bandwidth. If you are pulling less than 5 megabits per second down when you use a service like speedtest.net, it's probably an issue that none of us are going to be able to resolve. You're just going to need to get onto another network. The second thing is, depending on what application you're viewing from, you may want to try to quit that application, like Discord, for example, and come back in. This is a browser-based webinar platform. So if you're in the webinar platform, that shouldn't be an issue. But if you're using something like Discord or LinkedIn or something like that, sometimes the applications themselves present some issues. So try quitting them or coming back in. Depending if you're on a desktop, try making sure that you have enough bandwidth, that there aren't other applications open that are clogging up the stream. And other than that, inside of the platform, there is also a help button at the very lower left of the webinar system. You can hit this help icon to walk you through a wizard that shows you various things you can do to resolve your own issues. But if that doesn't work, just at the end of the day, put your issue that you're having into the chat area of whatever the platform you're on is, and I'll eventually get around to it and try to make sure that I can give you some help and get you up onto into the event and participating with the rest of us. If all of that fails, we are recording this event today, so there will be an opportunity to watch it later. It'll be put up on the DevHeads YouTube channel. So within probably a couple of minutes, actually, because we're streaming right there right now, there should be a version of this that's available for you to watch. So in case you can't figure out your stream, feel free to head back over there later on and check out the replay. I don't want to take up any more time. There are a couple of polls. We really encourage you to interact today, chat, and just really tune in as Hemal walks us through some fundamentals of power design. So with that, I'm going to hand it over to Hemal. Hemal, the floor is yours.
Thank you so much, Brandon, for the quick rundown. So today, without further ado, we'll start with powering the system. This is a continuation of the series that we have been doing. We started from the basics of PCB fundamentals, then we moved on to a session. We did a session on how to design a system, and now we are breaking down that presentation into separate individual dedicated sessions. So first one is the power. So Before we start, we'll have a little bit about introduction about myself. So my name is Hemal. I'm currently based in Dubai in UAE, and I've been in electronics design industry for last almost 8 to 10 years, and I've designed multiple products. Also went through the certification and go to market, and basically what I do is I designed PCBs and design products. So first of all, why join this session, and what do you get out from it? Number one is you can build a reliable product, and secondly, we are designing a carrier board based on the COM HPC standard by PICMIG. So you get to follow us on the journey, and this is a part of it, and understand what are the issues that can come up when you are having poor power design. So when you don't have a good design, you can have boot loops, you can in some cases also brick your device. And if you have a beautifully designed product that is everything is done perfectly, but if your power is not done in the right way, the rest of the design doesn't really matter, because it's the power that keeps the device running. So it's like the heartbeat of your system, and we need to make sure that when we are designing the power supply, we take into all of the gotchas and all the pitfalls that we should avoid when building a power system. So what we're going to cover today is we'll see how we can gather the requirements. Then we'll walk through how we can create a power budget. And once we have the power budget, the next step is to architect the whole power budget. So we go more deeper into the design. We'll talk about some PCB layouts and guidelines, and what things to watch out for when we are designing the power section. Also, once we have the product designed and we have it physically in our hands, how we can test it and troubleshoot it. So before we start on the power supply that we have, we need to talk about what does an ideal power supply look like. So you have a DC source, and you have a input impedance of 0 ohms. So we say impedance and not resistance. And we have a load which will have a certain load voltage and a load current passing through it. The important thing is that the voltage is able to supply the load with the stable voltage across all the frequencies in an ideal case. So what I mean by that is uh, almost 99% of the electronic products that we have today, or what we interact with or we are designing, are digital in nature. And the property of digital electronics is they are made of these tiny transistors, or and the CMOS, and they work on a constant voltage, but the current is not constant. The current consumption is not constant. So it's not like a fixed resistor. Uh, you have clocks in your system that take a certain amount of current, and those are they take current in a very discrete format. And this is even more true for wireless systems, where you see a lot of current spikes, especially when the device is transmitting. So you must have seen a lot of issues online around Wi-Fi modules, that the power supply fails when it's trying to transmit. It goes to a reboot, or it just you have other issues around it. So the important thing is that when we design a system, we need to make sure that our source is able to supply enough current and voltage at all the frequency that we need it to be. And for that, we will also need to talk about decoupling capacitors, that we'll talk about towards the end of the session, on what we should look out for when we are doing when we are adding decoupling capacitors for filtering our inputs, input power and output power. So that's all about the ideal power system. Next, what we start with is we understand the requirements. What do I mean is we list out all the loads that are there in our system. So first of all is the main processor, which is in most cases is the most power hungry, but it could be different. If it's a microcontroller design, it might be a bit different. Then we have all the peripherals attached to the system. So these could be your hard drives, your modules, Wi-Fi modules, 4G modules, if you have a USB hub, or any other sensors attached to it. Sometimes there is motors even connected to your system, which are driven by their specific drivers. And in a microcontroller, you could have a motor design as well. So we list out all the loads. Then we create a spreadsheet of all the voltage rails that are required. So in a system, if it's a small and a simple design, usually you would have 1 or 2 voltages present in your system. For example, you could have an input voltage of 5 volts, and your microcontroller product might be running on 3.3 volts. So in this case, you would have just 2 voltage rails, 5 volts and 3 volts. In other complicated cases, you might have higher voltages. So for example, if you think about the motherboard or a desktop PC, it has 12 volts as input. It has also 5 volt inputs and 3.3 volt inputs from the main power supply. So these are the different voltage rails. And there are other voltage rails on the motherboard itself, which are generated for other core, other force and things like that. After that, we create a power architecture. So we decide on how do we obtain this particular voltage rail. So we have an input, and now we need 5 different voltage rails. How do we derive this from the input? And when we are doing that, we are using converters, regulators, to get those voltage rails. So we need to make sure, also take into consideration how efficient they are and what is the power loss that we have to deal with. And based on the power loss design, we can also get an idea about the thermal design. A thermal design I will touch up on very lightly, because it's a separate topic on its own. And next, again, we have to, if it is a microprocessor or a system on module, these devices, they have a particular way of sequencing the power. So we cannot just turn on the power directly to these kind of microprocessors and system modules. They have a very specific timing diagram on what events should occur. We will take one example later in the presentation on one of the modules that need this power sequencing. So in this case, we probably need to have a separate microcontroller or a separate device that will help us in deciding what the power enabled signals would look like. Next, also we need to, what we take into consideration is the voltage tolerance of our loads. So for example, in case of our, let's say, SATA hard drive, it needs to have 5 volts, but if there's any tolerance of plus or minus 5% or 10%, it depends on the load. So we also need to understand and put everything into a spreadsheet. So Here's just an example of an example data sheet on where you can get various current rating, current characteristics. I think this is one from a STM32 controller. So that lists out all the currents on what we can expect the IC to consume if everything is turned on, and how much current it can source. So you would usually find this in the various data sheets and things like that on the amount of current it consumes. And by that, you can compute the power by the simple equation by multiplying the voltage and the current. So here is an example of a power budget for a carrier board. So put everything in a spreadsheet. We start by listing all the rails and all the components that use that voltage rail. What is the estimated current? And here I'm using peak currents, not the average current. You can also have separate charts for that. So you can have a peak power and average power consumption. And once we have this, we list it down. And then we go and start designing the architecture to decide how this voltages are derived. And then we come back here on this sheet and we input the type of regulator that we are using, what the efficiency looks like, and what the power loss looks like. And then we can add up all the power and all the power losses. So we get an estimate of what we are dealing with. So for example, this could be a couple of watts of power. So let's say around 50 watts of power. But there are other systems that can maybe even go to 200 watts if it's hundreds of watts. So here we have 3.3 volt, 5 volt, and 1.8 volts system. Now, the architecture is where we decide on the type of regulator that we are going to use. So let's say, for example, if we have a 12 volt input, and we need to have these 3 voltage rails, how do we derive them from 12 volts? So in this case, we have decided to use buck converters for 3.3 volt and 5 volt. And we have a 1.8 volt rail as well, but it takes quite less current. And also it doesn't need so much of power. So we can use an LDO in this case, which will be coming from 3.3 volt. And it could be used only in the place of the load where it is needed. So usually you can have on the layout, you can have a centralized or a distributed power system. But usually it is a combination of two, where you have your switchers in one location, and then if you have a low voltage LDOs, if they are not used in many places, then you add it at the point of the load. So if the other components would be using 1.8 volts, we could also use multiple LDOs, because LDOs are comparatively cheaper than the buck converters, and also has a low component count, so they're a bit easier on the BOM. Next, we look at in the architecture, we look at the sequence controllers. So it's usually a microcontroller that controls the inputs and outputs of the enable signals. So it monitors certain voltages, and based on those, we have a logic on when we want to turn on the enable. So for example, if we have the input as the power button, so as soon as the power button is pressed, after a certain time, you can start enabling the signals to the power enable lines of the regulators, so that they start working, and then they can supply to the currents. And next is the load switches. The load switches are very useful in cases when you don't need to power everything at once. So for example, I'm going to go back to the power budget sheet. For example, let's say the 4G module and the camera and the Wi-Fi. There are certain devices that does not need to be powered on all the time. So you could have, let's say, the camera. You could turn off the power to the camera, or turn off the power to the Wi-Fi card if you already have a 4G connection, or vice versa. You can turn off the 4G module when you already have a Wi-Fi connectivity. And if you lose the Wi-Fi connectivity, you can bring up the module. So this type of arrangement helps us to save the power, and also make sure that we have enough reserves in our from the power supply, so it's able to supply all the sufficient without any issues. Other application of load switches is in changing the voltage. So we'll talk about the inrush current is an issue that we'll talk about in the later down in the presentation. So load switches can also used for helping in mitigating the issues with the inrush current. This is fairly easy. We have on how we can find the efficiency of a regulator, or is the same works for the switching regulator as well. Is basically you have output power divided by the input power, and that's how you get the efficiency. So in terms of LDO, 50% is the maximum that you can get. Is usually less than 50% for LDOs. But for switching regulators, it depends. It can go from like 80 to 95, 99% of efficiency based on how much load it is rated for. And because they don't have constant efficiency across all the output voltages, usually there is a curve. So it goes from like 80% to 95, 99% in some cases. Next, after we have decided everything, we draw a nice design power tree. This helps us in visualizing how the voltage rails are coming to picture, what kind of topology we are using, and whether we're using LDOs and switchers. So it gives a very good idea from a top-down view on what we are doing, and also helps anyone else working on the system understand where the power is coming from, so that they can also take into consideration if there's anything that they need to be careful about. Centralized and distributed power topology, I sort of touched on that. Basically, you have the conversion happening at the input side of your PCB, and then that's one way. Or you can have your input voltage go all across the board, and then changing the voltage rails to the particular voltage rails at the load. So it depends on the type of system that you're designing. Usually it's a mix of both, where you have mostly centralized and distributed for one or two rails. So here's just a very simple example of a power tree. You can have it in a text way, or you can have it in a block diagram, however you wish. But the concept is such. You have a 12 volt, you have buck, then you have it gets to 5 volts, and from 5 volts you have an LDO for 3.3 volts, and you have another LDO that goes to 1.8 volts. And this is just a very basic example that you can. It depends on how your system is, on what type of loads it's having. We cannot really talk about the power without the power inputs. So right now we have been talking about the outputs and the voltage rails and things like that, but the power input is also as important. So what are the sources that are possible? These are usually, if it is a smaller device, it's usually 5 volts from a USB, or it could be a battery from a LiPo, or it could be a combination of both. And you have a charging circuitry, so it runs off USB, and then when you don't have it, it runs off the battery. Next is so you have 5-volt and battery sometimes in conjunction, and other times you have 12-volt barrel jack, and you can also have a PoE. So you are getting power from the Ethernet, which would have a higher voltage rail of 48 volts or 24 volts, depends on the type of PoE that is being used. And you can also have a solar input as well. So you can have, if it is a system which is in the field, it could also use a solar power. So you need to make sure how we are going to select the input power based on the power that is available. And this selection of power is called power ORing. So for example, when you have the most simple example is your mobile phones. They are usually running off of battery, and then when you plug in your USB, they are charging while you can still use your phone. So when you plug in your USB, the power gets divided to your phone, and the rest of the power gets to your battery, which is used for charging it. So what is happening there is called power ORing, and that's how you are changing the path of the power on which source is providing the power to the system. Next very important part is with your inputs is you need to have protections. When you're giving any input to your system, um, you have to assume that it could be something which is not rated for it. So how do you protect your system from that? One of the protections is reverse polarity protection. So if you have plus and minus reversed and you plug in your system, it should not burn the system. You should not blow it up. It should just stop the power supply to the system so it doesn't turn on. There are various ways of doing that. You also need to have a fuse. So if there's something goes wrong in your system, it should not damage the input power supply. And of course, you need to have filtering, which will make sure that a clean power is coming to your DC-DC converters or LDOs. So this is a very rudimentary example of how your power ORing works. It's usually two diodes. So you have two voltage sources coming in, and you have the load, which is the resistor here. And when you're doing the diode-based ORing, it's usually the voltage that is higher gets to the load, while the less voltage is not used. So for example, in this one, if you have 12 volts and 5 volts coming into your system, this diode will conduct only the one with the higher voltage, and the other one will get the reverse bias, so it will not conduct any current. Again, there are different ways and different specialized ICs available for this, which helps us to do the power ORing. In some cases, you might also want it to have it reverse. So you want to select 5 volts in case of even if the 12 volt is available, and then only use 12 volt when 5 volt is not available. So there are various methods of doing that. But just be aware that this term is called power ORing. Protections, I think I already went through this. Is you have to have reverse polarity, you have to have fuse. One I didn't talk about was the transient protection. This is very important when you're designing any sort of automotive system. So let's say when you are designing something for like a CAN bus reader or a ODB port reader, usually you think that the car voltage is 12 volts coming from the battery, but when the car starts, there is a lot of transient that can go up to like 60 volts as well. So we need to make sure that during this period the transients are suppressed and it doesn't damage the rest of your product. And the last one is also over voltage protection. So if you have a rated voltage of up to a certain voltage, because every converter has a upper limit on what they can convert. Usually you have an input range of depends on the converter, but something, let's say an example like 5 to 24 volts. But if you are supplying 40 volts or 48 volts, it should just shut down, and you have to make sure your regulators have that protection inbuilt, or if not, then you have to build those protections yourself, just to make sure your devices are not harmed. Right. So now we'll talk about the decoupling capacitors. And in the beginning, I talked about the ideal power supply, saying that it should be able to supply the power to your load at all the frequencies, but that's not the case. And here, what I'm showing is this graph, by the way, comes from this website called KSIM, that is KSIM. I think it's a simulator from Kimet, which is a capacitor manufacturer, but now it's taken by Yageo. But the website is still there, and it's very, very helpful. So when you have various capacitors in parallel, the capacitor impedance changes. And we usually know that a capacitor is inversely proportional to the impedance of the capacitor is inversely proportional to the frequency of operation that we can see here. So the higher the frequency of operation, the impedance decreases. But at a certain mark, the capacitor starts to act as an inductor, where your impedance rises with the rise in frequency. And in this example, I've taken three capacitors which are in parallel, and one of them is a tantalum capacitor, the red one. So you see how the frequency curve of this tantalum capacitor is. So at a very low frequency, at around around, let's say 5 or sorry 2 kilohertz, it starts to act as an inductor, versus the other two, the yellow one and the blue one, they are overlapping because they are of the same type, which are the ceramic capacitor. And in the gray line is what you see is the impedance, the combined impedance of the when you have all of them three in parallel. So very important on if you are you should know how at what frequency your load is going to take the current at, and you need to make sure that your capacitors are not acting as inductors. So if you use tantalum capacitors in some high-speed design, that's probably not a very good idea because of this graph, because the tantalum capacitors will become like inductors in when you are using it in a place where you shouldn't be using it. So yeah, this is about the decoupling capacitors. Next, we'll talk about the sequencing, and we'll also see an example after this. So when you have, when is this needed is when you have like an on-off button. So if you have a, let's say you're working on a robot that you need to turn on and off, but you cannot just turn on and blast power to all the parts of your robot. You probably just need to have the power to the logical side first, and then when the logical part decides, okay, it's safe to power the motors, then it can power the motors. So this is a good way to sequence your power. And also sometimes if you are designing a smaller system on module, or a smaller SBC, there are modes which is called a sleep mode or recovery mode. You need to take care of those on how, which power supplies to turn off and which to keep them on. And if you hit the reset button, how should the power sequencing should happen, and things like this. So it will help in a safer shutdown and startup. Otherwise, you can power it just by giving power to all the rails, and it will work for some time. But then after a while, it might get unreliable. So that's not really advisable. And you can also use this supervision and for monitoring or enabling loads which are optional, that you really don't need at all to be on at all the times. So for example, if you don't have an HDMI connected, you can just have the HDMI subsystem not powered up. Or same for Wi-Fi, if you already have Ethernet connectivity, you don't need to have, you can also shut down your 4G module if present, if you already have Ethernet connectivity. So these will make sure that it's not from a point of going green and saving power, but it's just to make sure that the power supply system has reliable amount of juice to give it when it's needed. So here is just a simple example of a power up sequence of a Jetson Nano board. And so you have your VIN line on, and your shutdown request is also high. And when you press the power button, so this is the sequence that happens when you turn on the system by pressing the power button. So you monitor your power button as soon as it goes low for a certain amount of time. Then the power enable line goes high. And then after you have to wait for 14 milliseconds and let go of change the input, change the output of the system reset to high. And then once this goes high, then later on the carrier board supplies will turn on. So this blue arrow is related. So the power enable becomes like your input. So these are all signals, and you have to monitor the signals coming from the system on module, and based on that, release or make the certain signals high or low, depending on the specified time intervals. You also have a power down sequence as well, which I've not listed here, but you get the idea on how this works. Some other microprocessors might have a more complicated power up sequence. So when you have a microprocessor, you have to have more. There are more of these timing diagrams, because there is core voltages. You have to supply the power to the RAM, and you have to turn on the RAM before you turn on the microprocessor, just so that you don't have any garbage data or anything like that might cause some issues if you do it the other way around, when you turn on the microprocessor after and then you turn on the RAM after you have already powered up your microprocessor. Next, we'll go a bit deeper into the layout on what we should take care of. The first one is the most easiest and the most obvious one, is your trace width has to have the current carrying capacity that you are intending it to carry. So if you want to carry 2 amps of current, there are multiple calculators available online. I always use this one from Saturn PCB toolkit that helps to decide these kind of parameters, and also how thick your PCBs are, the ounce of PCB that you're using. And that's the most basic one. Or you can also use polygons, so you have even more bandwidth with your current carrying capacity. In terms of the power trace, it's not only let's say you have a trace that is going to carry 2 ampere of current, but you have to have some overhead on top of it in order make sure just to have the buffer, and also to accommodate for the inrush current. We'll talk about that in just a few slides again. Next is how you place your inductors and capacitors. So it's very important to make sure your current loops are very small and very tight. I'll show you an example on how we of an example of a current loop that you can see. If you don't place your capacitors and inductors of your switchers properly, it can lead to a lot of other issues and things like that. Next is the noise isolation. So this is usually done by grouping or keeping the voltage converters in a corner of your board, and logically dividing the ground plane. We don't have to split the ground plane or cut the ground plane, um, but logically just have it in one corner, so it's easy to manage this sort of current loops in the ground plane and ground bounces. So we keep and we make sure there's no critical traces are going through this power section, so that can interfere with our signal. So we try to keep it away from other stuff as possible. The layer stack up also plays a very important role on how your system performance would be. Again, a layer stack up is a topic on its own, but for your requirements, you probably need to check what sort of rails you're using, and how many layers you want to use, and how are you going to distribute your power. So for example, if you just have a majority of your system is working on 3.3 volts and only one or two components are using 5 volts, you can have 3 volts on one of the planes in your layer stack up, and you can route the 5 volts as a trace. But it depends on your particular example, how you want to do that. Next is your PCB itself. Because it has a lot of copper and you are using these planes, it also acts as a thermal sink. So based on the size of the PCB, based on the power loss that you have calculated, you can calculate how much watts of power is going to be wasted, and can the layer of the copper will be able to take in that heat. Would that be enough? And if not, would you need an external heat sink to do that? And many times it's not really advisable to send your thermal to your PCB. If it's too hot, then the PCBs can deform, or it might become a bit plastic, and it can have a effect on a longer term. So immediately it would work fine, but it would the life of a product would probably get shortened. The next is having the test points. So very important is you need to have a lot of test points, at least one for each rail, definitely, so that you can monitor the voltages, whether they are on or off. You can measure the amount of noise and ripple in those voltages. So we'll talk a little bit about the ground bounce. Ground bounce is an issue that happens mostly in the switching regulators. Here I have a example of a step-down converter. So you have two cases. One is blue and one is red. So let's focus on the two loops which are near from the CV in to the load. So let's just focus on that part. The V in and inductant voltage will assume it's not there, just so that it's simple. So when you have switch in position 1, you have the red trace going across your circuit, and when your switch goes to position number 2, you have the current loop in your green and in your blue arrow. So what happens is when the switch happens, there is a certain amount of current that flows between the 2 points, because when your inductance changes, or when the current through inductor starts or stops, the and they induce a voltage. So in this case, you have these two loops which create this ground bounce. So when you have the current flowing through a reference plane, so you have a point in your system which you have defined as ground, then the voltage across all the places on that reference should be 0 volts. But when you have current flowing through that because of uneven layout, or because of these currents collapsing, so you have current flowing in the ground plane. The current flows because of there is a voltage difference, and this voltage difference is your ground bounce. So it either raises the voltage from 0 volts or lowers it below 0 volts. Either way, it causes issues with your anything that is referenced to that particular point. So here I just want to have like a one poll, that when you have a system, which point should you consider as your ground? Should it be the negative supply of your DC source, or the low end of your load? I think the poll is up. You can submit your vote over there. I think it's already there. We'll come back to this at the end of the session. You can leave your votes there if you like. So how do we fix this? So imagine we change the switch with a semiconductor or a MOSFET, and usually you have a diode across it so that the current flows only in one direction. So this is how we solve the issue, where the change in the loop area is very small, and in this case your ground bounce is minimal, and all your inductances and the field lines, the magnetic lines, they are tightly coupled in a smaller loop, so that the ground bounce doesn't happen. I think I'm gonna go a little bit fast because I think we need to have some time for the Q&A. So next is testing and measurements. We do testing and measurements for all the things that we already designed for. So we find how much is the ripple voltage, so we know how much is the noise. So, and we need to make sure that we are in the allowed voltage tolerance. What's the efficiency, the real efficiency of our converters? What is the inrush current? What is the functioning test is working? So you have the voltage rails that you actually designed for. Is the reverse polarity working? Protection is working. If your short circuits or protection are working, your fuse is fine. And if you apply a voltage higher than the rated voltage, that's not damaging your system. And common errors in troubleshootings are you have an inrush current. So this inrush current is basically a spike in the current consumption when you turn on the system, which is really not good to have, because the amount of current that goes in that peak time, you might not have designed your PCB trace for that current rating. And you need to make sure there is no ground bouncing, and your sequencing is working fine, and your noise and your ripple voltages are under your control. So here's an example of an inrush current, and usually we say that we should add capacitors. The more capacitors, the better, because it will help us filter our currents and things like that in a better way. But I have another poll here. If we want to reduce the inrush current, is increasing the capacitance advisable, or decreasing is advisable? So here we see an example of when you're in the first graph, when you turn on your supplies, the peak current, it goes to around 3 amperes. and it's charging a, let's say, a 47 microfarad capacitor. So when you have a lot of capacitors in your system, when you just turn on your power supply, all those capacitors starts to get charged. So at that certain point, it is like an AC input. So all the current gets absorbed in these capacitors, and they start to charge up. And this causes a huge load on the power supply, where it takes in a lot of current in a very short amount of time. And once they are charged up, the load current goes back to the average. So as I said, if you have made your system to supply 1 ampere of current, and you say, okay, I'll put a buffer of another ampere, so you make a power trace for 2 amperes. But if your inrush currents is very high, if you have a lot of capacitors in your system, this inrush current can go to 3 amperes, and then this over time can damage your power trace. It can burn the power trace, or it can momentarily heat up the power trace, which is not really advisable. In the second graph, there is this, you have your stable voltage of 3.3 volts, but suddenly you turn on a module, let's say a 4G module, which has a lot of capacitors on it, let's say. Then it would also try to take in a lot of current at in a very quick, in a very short amount of time. And this will cause the voltage rail to droop, and it will go down to so in this case, it goes down from 3.3 volts to almost 1 volt during this, when you just turn on the load. So this is the problem with the inrush currents. And this can cause issues to other parts of the system, which is already expecting this 3.3 volt system. So this can lead to a reboot or a brownout, and all sorts of nasty things that can occur. So in order to fix this inrush current, there are methods that you can use is by using slew rates, load switches with less slew rate. So they basically turn on the voltage in a very slow manner, so that this kind of inrush current can be reduced. So I think this about brings about the end of the presentation. We have these resources listed out that you can use when you're designing your power system. Is from the TI, you have the vbench website that you are able to simulate currents and things like that. You have power tools from Analog Devices. I already mentioned the KSIM, where I did the decoupling, where I showed the decoupling capacitor chart. So you can mix and match those when in your system, how they are reacting, and you can see the impedance curve. And there are app notes that you should always go through, which are very, very helpful. So that's about it. That brings me to the end of the presentation. And Brandon, let me know if there are any questions.
Sure thing. So my first question here is what's your preferred tool suite? Yeah, what do you use to do your measurement and analysis when you're designing, and why? Why do you recommend that?
So I try to use tools which are free, and I also use these forums, web forums as well, and also use design reviews a lot. So let's say if you need to design a system, we can start with a power tree, and then for the let's say it also depends on what kind of components that we are using. So if we are using TI, I would definitely use the TI workbench, vbench, and try to simulate all the inputs and outputs. So that's one way. And for designing I use this Saturn PCB toolkit. That's an excellent resource for a whole lot of other things to size your vias, the trace width, and make sure that your trace doesn't also has an increase in temperature and things like that. And I use this KSIM as well for doing the analysis for the impedance of the capacitors. I hope that answers the question.
Yeah, great. Also, before we sign off, we should go through the poll results. So the first poll, which was which point should be considered true ground, either the negative terminal of the DC source or the low end of the load. What's the answer?
So it should be at the low end of the load, because that's where your load sees your that's where you should measure your voltage from, because when you are doing at the end of the negative terminal, as I mentioned, there could be ground bounce in between. So your true ground as your reference should be always at the end of the load.
So that's something we need some brushing up on, guys, because we had two correct answers out of 8, and there were only 2 options. So why do you think that that's a commonly misconstrued or misunderstood concept, Hemal?
Well, because from the academics and from all that studying that we do, we really don't talk about the practical aspects of the design. And when you are designing real boards and making real power supplies, you understand that these issues of ground bounces can occur, which can basically change the reference from what you're measuring. So from the negative terminal, you might be measuring your 3-volt system. It might be showing that, but if you measure it from the low end of your load, you might see that there are some ground bounce effects where your ground is shifting. That means the voltage on your load is changing. So this was also not very apparent to me in the beginning. I also used to measure it from the negative terminal always, but I found this in an app note from 2007. It was by an analog design engineer. So that was quite an eye-opener. That's why I had it in the poll, because it's something that was something that I learned something new, that what he's saying is right. So
great. The second poll, in order to reduce inrush current, should you increase or decrease capacitance? The options were increase or decrease.
So you should decrease your capacitance, so that the less the capacitors, the less current is there to charge the capacitors. So you don't have that peak in the current. What's the answer? The people have taken.
Everybody got it wrong. So I think,
Right?
I think we need some more.
Sure.
Power
No,
session.
it's really even I got it the same answer. It was the wrong answer, but again, I when I read this, I was going through the TI app note. I mean, you can just Google TI app note of inrush current, and it will tell you all of that. The graphs were also I picked up from that app note, and that's also something I learned that day. Because when we are designing systems, it's like, yeah, add capacitors, it's what's the worst that can happen? You're just adding capacitors, not gonna cause any issues. But not really the case. It does has an effect. So when you're adding capacitors, make sure you have adequate amount of capacitors. Just don't add as you know, throw in a couple of microfarads of capacitors. It's fine. But when you're designing your system in a proper way, I think you need to read more app notes. There's so much of treasure of knowledge in these app notes.
That's great. Well, that brings us to the end of the time that we got today. Some great stuff as always, Hemal. Thanks so much for the insight. And it sounds like the group, the collective, could use a little bit more brush up on power design. So hopefully we'll have some more content on this in the near future. Just want to let everybody know that there is another event coming up tomorrow. It's a hack session on using MQTT for, oh, hey, Dharmic, on using MQTT for smart home lighting control. So you want to check us out for that. And then in a couple of weeks on Friday, there's another session on using NICs. So for embedded development. So Dharmic, since you're on the line, did you want to jump in and ask a question? Oh, I guess not. Here he's gone. So anyway, that is it for us for today. We really appreciate all of your time and joining and participating. And we will see you in the next sessions, and then also in the community, which you can go to at discord.gg/devheads. So thanks a lot. I hope you guys have a great weekend, and we'll see you in the server.